Good morning. I'm sorry about all the issues that I was having with the internet earlier. I will go ahead and record my notes for class today and get those posted on D2L. Just a reminder that we did change the due dates for our quiz and our homework 7. So quiz 6 is due this Wednesday night, March 25th by 11, and homework 6 is due Friday night, March 27th by 11 p.m. I'll see if I can get another system worked out for giving lectures remotely. But for now, I will record our lecture notes for today. So we will be looking at parametric and non-parametric tests and confidence intervals for simple linear regression. So we'll work through confidence intervals and hypotheses for intercept and slope. We'll also be looking at non-parametric tests. So we'll be looking at permutation tests and bootstrap confidence intervals for simple linear regression. All right, so let's kind of get started with just looking at our confidence interval and hypotheses for intercept and slope. The confidence interval for intercept and slope of a simple linear regression follows the same general form as any confidence interval. We're looking at our estimate plus or minus our multiplier times the standard error of the estimate. The multiplier times the standard error is our margin of error. So when we're finding a confidence interval for the true y-intercept, beta naught, we're looking at B0, our estimated y-intercept, plus or minus the t star multiplier with n minus 2 degrees of freedom, times the standard error of the y-intercept. When we interpret the confidence interval for an y-intercept, we're looking at when our explanatory variable is 0, we are X% confident that the true mean of y, the response, will be between our lower value and our upper limit in our units of y. For a y-intercept, we're not interested in the hypotheses for this study. Looking at the confidence interval for the true slope for beta 1, we're going to find our confidence interval again by using the estimate for our slope plus or minus the t star multiplier from the t distribution with n minus 2 degrees of freedom times the standard error of slope. For the interpretation for the confidence interval of slope, we're looking at a 1 unit increase in x. We are 95% or x% confident that the true change in the mean of y will be between the lower limit and the upper limit units of y. When we're testing slope in symbols, our null hypothesis will be that beta 1 is equal to 0. The true slope is equal to 0. And the alternative, that beta 1 is not equal to 0 for a two-sided test. In words, there is no linear relationship between x and y in the population. For our alternative, that there is some linear relationship between x and y, the explanatory and the response in the population. We can also look at one-sided tests where beta 1 is less than 0. There is some negative linear relationship between x and y in the population. and beta 1 is greater than 0, there is some positive linear relationship between x and y in the population. For our parametric hypothesis test and confidence interval, we can calculate our test statistic for the slope coefficient by hand or from the output directly. Under certain validity conditions, the distribution of the slope coefficient under the null hypothesis will be a t distribution within minus 2 degrees of freedom. To calculate our test statistic, we'll use our value of slope, b1, divided by the standard error of the slope. Please note that the test statistic t is not equal to the t-star multiplier. These are different values. T is the test statistic we'll calculate from our data. T-star is the multiplier from the t distribution within minus 2 degrees of freedom used to find a confidence interval. Let's look at a study. Researchers interested in plant diversity collected data from 22 islands off the northeastern coast of the United States on a variety of factors that may be related to a variety of plants on the island. Specifically, researchers would like to determine if there's an association between the number of available soil types and total richness of plant species on the island. So our two variables here, total richness of plant species, tot.rich, and the number of soil types, soil.types, is our other variable we're looking at. So to fit a simple linear regression model, we're looking at our linear model of y distributed as x, and we're looking at this data set, plants. Remember that when we find our estimated line of regression, we're taking the estimated y value, total.rich, and we're taking our estimate for the intercept, 143.91, plus our slope times the x variable, soil types. That's our estimated line of regression. Soil types is our slope. So this is our estimate for our slope. This is the standard error for the slope. So to find our parametric test statistic, we'll take t, the value of slope, divided by the standard error of slope. So 14.153 divided by 2.362 equals a t-value of 5.991, which is given in our R output. Notice that the p-value for this test is very small, so we'll consider it less than 0.0001. So now let's look at calculating the parametric confidence interval by hand. Notice here that we have code from R showing the quartile for 0.975. So this is finding the t-star multiplier for a 95% confidence interval. When we look at our t distribution, 95% would be within the 2.5 percentile and the 97.5 percentile. So using the quartile 0.975 gives us the multiplier with 20 degrees of freedom. So we have 22 for our sample size. And this is the multiplier we're going to use to find the 95% confidence interval. So using R as a calculator, we're going to take our value of slope plus or minus, that's what this code here gives us, the t-star multiplier times the standard error of our slope. So this gives us a 95% confidence interval of 0.9226 to 19.08. We could also use code to get the confidence interval directly using this code in R. And now we can see the 95% confidence interval for our y-intercept and the 95% confidence interval for the true slope. To interpret the y-intercept, we'd say for an island with 0 soil types, we are 95% confident that the true mean number of species is between 7.39 and 280.43 species. To interpret the confidence interval for slope, for each additional soil type, we are 95% confident that the true change in mean number of species will be between 9.23 and 19.08 species. We can also visualize the confidence interval and the estimated regression line using a term plot from the effects package. This is the same function we use for visualizing the ANOVA model, but it is smart enough to know when we want to visualize a simple linear regression model. So this term plot or effect plot, it's a terms plot because it's not random assignment, shows the estimated regression line with 95% confidence interval bands for the means for each soil type. It's another plot that we can use to look at what we're seeing in this study. Looking at non-parametric tests and confidence interval, we can use a permutation test for simple linear regression if there is evidence against the normality of residuals and no influential points. Assumptions. To see if we have evidence against these assumptions, we need to look at diagnostic plots. For the permutation approach, we're going to shuffle the explanatory variable and compare the observed slope to the simulated values of slope attained from the permutations under the null hypothesis of no linear relationship. So here we're finding our Taubes value and we're assigning the slope. So we get a slope of 14.15. This is our estimated slope. We're creating 1,000 permutations of our slope, assuming the null is true, assuming there is no linear relationship between our variables. So here we can see our histogram and our density curve of our T-star. And this shows a histogram of all the different simulated slopes from each linear model fit. The red line, the red lines are at the plus or minus slope values. So here is our 14.153, the slope value, our observed slope, and this is negative 14.153, our negative slope. So our permuted p-value is essentially 0, so we'd say that's less than 1 out of 1,000 permutations. When we think about an interpretation of a p-value, we're looking at our probability of seeing our statistic, or more extreme, if the null is true. So there is a less than 1 out of 1,000 chance of observing a slope as or more extreme than 14.15 if there really is no linear relationship between soil types and number of species in the population, if the null is true. So our p-value, there's less than a 1 out of 1,000 chance, is the probability of our statistic observing a slope as or more extreme than our observed slope value, 14.15, if the null is true, if there really is no linear relationship between soil type and number of species in the population. When we think about a conclusion, we're talking about how much evidence we have. So there is very strong evidence, since this is a small p-value, against the null hypothesis, that there is no linear relationship between soil types and number of species in the population. And this is based on our slope of 14.15 using a permutation test and a p-value of less than 1 out of 1,000. So there is a linear relationship between these variables. When we use a non-parametric test to find our confidence interval, we use a bootstrap confidence interval. The bootstrap confidence interval can also be useful when there is evidence against the normality of residuals and no influential points assumption. the same as for the permutation test. For the bootstrap approach, we're going to resample the original data with replacement and calculate the 2.5 and 97.5% quantiles to obtain the 95% confidence interval. Here's the R code for that, and here is our 95% confidence interval for the true slope. So 10.76 to 23.22. Here's the histogram and the density curve of our bootstrap distribution. The blue lines are at the confidence interval, lower and upper values. At the quantiles. The interpretations are the same for parametric and non-parametric